tendency. Hi, I'm Ken Adams. I'm a geology professor at Desert Research Institute in Reno, Nevada, and I'm making a series of these videos just to kind of talk about type of landscapes that are out here and how you study them and how you think about them, or how I think about them anyway. And I find it pretty interesting. Hope you will too. And so right now we're at a place I refer to as the Salt Wells Beach Barrier. It's out in the east of Fallon in the Carson Sink at the base of the Lahontan Mountains, which are behind me here and to my right, your left. And this is a really interesting feature here. If you were the last stops we went to, we were in, where were we? Basically at the north end of the Boone Jugs on the Spit, and that's also at about 1,200 meters, and we're standing right here. The crest of this thing is 1202 or so of this east-west linear ridge. And so it's the same elevation as those beach deposits were where the Wono tephra was encased, 27,000 years old. But there's evidence that this feature, this beach ridge, a lake of the same size, was only 850 years old. And how do we know that? Well, worked at it. So it started with Jonathan Davis. Actually, no, it started with Roger Morrison. This was what he named his Fallon 1 shoreline, which he had a name for this series of late Holocene lakes he referred to as the Fallon Lakes. For obvious reasons, we're near Fallon. And he envisioned them forming these sort of concentric rings of shorelines starting, this is the highest one at about 1,200 meters, and receding down towards Carson Lake, which is off to the south here in the Carson Sink. And the lowest ones were like 1180, 1185, something like that, which is near where the lake has got out here in historical times. And so Morrison named these the Fallon. This is the Fallon 1. And then in Jonathan Davis's 1978 monograph on the tephrochronology of the Lahontan Basin, he noted that there was a tephra in this deposit, and I'll show you that in a minute. But that tephra is one of these things. Locally, it's called the Tarupa flatbed, because I guess this flat expanse out in front of us is a Tarupa flat. Hold on a second. Indy, come back here. Come on. He's getting a little far away. Not that there's much out here. No snakes this time of the year. Although it's pretty warm today. Anyway, the Tarupa flatbed. It is equivalent, it's one of these monocraters tephras that were erupted anywhere from about 500 to 2,000 years ago. Monocraters being that little volcanic mountain chain on the south side of Mono Lake. And also, or Inyo craters, one of those, from one of those vents down there. And so it's widely dispersed up here, or not, it's actually usually pretty thick, but you find it in a lot of different sedimentary environments. It's in, well, this is a beach ridge, I think. Some people, originally thought it was a sand dune. They still might. Where am I going with this? Okay, Tarupa flatbed is found in alluvial fan, sand dunes, beach deposits, deep water lake deposits in Walker Lake, fluvial deltaic down at Walker. Indy, get over here. Come on. So here it is in a beach ridge. And so the crest of this beach ridge is sort of pretty lumpy, and there is certainly some sand moving around up here and being deposited, almost little coppice type dunes that you see here with little little plants sticking out of the crest of these things. And so the surface of this feature has been built up and probably eroded and built up and eroded by aeolian processes, i.e. sanding. It's going to get loud here in 20 seconds because the military helicopters coming by low and slow. But cost of doing business out here. Yeah, there is sort of aeolian processes, but the stratigraphic architecture of this feature, this landform, can be figured out from the shape of, well, how this particular tephra was deposited and how it lays in here, and we'll go look at parts of it. So we're looking down the crest. We're looking east down the crest of this feature, and it's rounded. It's positive relief on the front. There's a playa, which is Churupa Flat, that is probably about 5-8 meters below the crest of this feature. On the back, there are some old dunes that are vegetated, not very active. Not sure where all these boulders came from. Probably not imported. I'm not sure why anyone would do that. And then off to the west as well, you can see the crest of this feature, and I'll walk around. There's a road cut. The road goes right through this thing. And so you can see that it is a ridge, it's sort of a linear pile of sand. And this tephra, and I'll show an outcrop or two of it in a minute, sits in here like this. It's dipping backwards, very similar and I think identical to the backsets we saw at the Boone Jug spit, where the tephra was, the much older tephra, but at the same elevation. And so it's sitting in here like this, sloping to the north. And you can trace that tephra, I think, over 1.5 kilometers from down at Macquarie Road, which is the next road to the west, all the way down to the tip of this thing. It's a spit at the tip. It's free, and it penetrates out into the playa, and that tephra just sort of plunges right down into the playa. And so the significance of that continuous bed that is in the same orientation, the same attitude, all the way along this linear ridge, means that surface, because tephras represent an instant in time, they're isochronous, that was the active surface. That was where active deposition was going on at the time of that tephra, the time that the tephra was deposited. And so it also, it kind of pins the stratigraphic architecture. This is a pile of sand with beds in it that are dipping off to the north. And so there are certainly dunes out here in Churupa Flat, both on the mountain, you know, kind of migrating up near the mountain front here, but also out in the flats. And but they're all much smaller than this in terms of their how long they are. And again, you know, when they were active, their slip faces would be much shorter, just because they're small, kind of more stubby, not so linear type features. And so I think the best explanation for this is that this is a beach ridge that there were waves breaking over the crest of it at the time that this particular tephra was deposited. And so the age of that tephra is also the age of the shoreline, and vice versa, right? Because they were made with each other. And so in Jonathan Davis's 78 monograph, he talks about shorelines being inscribed on the front of this feature, okay? And I would sort of take it a step farther and say this is actually a shoreline feature itself, and was forming as a shoreline feature at the time that the tephra was deposited. He just claimed that the lake at this elevation should have been or was younger than the tephra because it crosscuts it. But I think they're more tightly intertwined than that. Not just younger, they are the same age. So let's go look at this tephra. Come on, dogs. Lucy's always so good about coming right back. All right. So I took the liberty to dig this out a little bit. We'll go search out for some more so you'll be convinced that it is a continuous bed. So it's very fine sand. Dig it out. And so this is the one of the monocraters, locally called the Trooper Flat. And not in this particular little exposure, but one within 100 meters of here, I pulled out some charcoal right from about that far away, that far below that tephra. And it turned out it was 812 years old. That's radiocarbon years, which calibrates out to some ridiculous range like 900 to 650 years before present. And so that's not entirely satisfying, but since that was all that stuff was published in 2003 in Quaternary Research. And so since then, gosh, 12 years ago now, started using tree rings to add sort of detail to try to refine the age of this lake that was very large. You know, I just mentioned that it was at 1,200 meters in elevation, but you look out and all of this was covered with water. And as a matter of fact, this lake was 3,000 square kilometers. It extended all the way up to Lovelock. And, well, it was about 20 meters deep in the Carson Sink, so 60-something, 70 feet deep, pretty deep. And had a volume of maybe 35, maybe 40 cubic kilometers, which again, that's a lot of water. And so I was really interested in knowing, well, when exactly, what is the age? When did this happen? How long did it take? Okay, dude with a stick, he'll find a stick no matter where we are. All right. Ready? Go. Okay, back to geology. So I wanted to know, when did this lake occur? Okay, one more. And so I started using tree rings to help with that, and they've helped tremendously. And so independently, this guy Ed Cook, who is the author of the one of the lead author on the North American Drought Atlas that later became the Living Blended Drought Atlas, he came up with the Living Blended Drought Atlas, which is a gridded representation of tree rings and year-to-year moisture, relative moisture at a place throughout North America for the last 2,000 years. And so based on the tree rings that occur in this region, during the medieval climate anomaly, which lasted from about 900 to on the order of 1,300 or so, I'm going to set this down. So, during the medieval climate anomaly, there were two very long, prolonged droughts, and they're now referred to as the Stein mega droughts because Scott Stein was the one who first sort of documented the occurrence, but the timing of them and their spatial dimensions of these droughts that lasted longer than 100 years have been really detailed by the Living Blended Drought Atlas, which is composed of a gridded representation of moisture-sensitive tree ring chronologies. Okay, dude, you're distracting me. Go on. So, dude, out. You're distracting. Where was I? Tree ring chronologies. So, we had the Stein megadrought one, which lasted from I'm going to not get these numbers right. 832 to like 1074. No, that's too long. Anyway, it lasted more than 100 years, but it ended in 1074. And then from about 1075 to 1121, there was a pluvial period, a very wet period. And then beginning around 1122 AD, you went into the Stein Mega Drought 2, which also lasted about 100 years, or more than 100 years. And so you had prolonged drought, a very wet period, not as long, but 46 years, and then another prolonged drought. And this is all detailed in these tree rings, and it's very convincing evidence. And so when you look at the calibrated radiocarbon age range that is possible from the charcoal that I extracted from right beneath here, the only significant prolonged wet period was that period, that 46-year period right between the two mega droughts. And so that is now, what we refer to as the medieval pluvial. And so it's very interesting and sort of scary that the climate can lock into these states in this part of the world, like very, droughty for decades, more than 100 years. And, if this lake that was this big came back, it would also be a big problem, but most people aren't as concerned as about too much water, because after all, we live in the desert, so it doesn't happen very often. But it happened 850 years ago. And so the way I look at it, and a lot of other people do too, is because the climate boundary conditions for our planet have been in place for 5,000 or 6,000 years, the last 5,000 or 6,000 years, the current climate boundary conditions, what are maybe some people would call modern boundary conditions, anything that has happened during that period could happen again, in the future. And so there could be these very long, prolonged droughts. There could be long, prolonged wet periods. There's most likely will be. Will we be around by then? I don't know. And so right now we're in a 3-year drought. It hasn't done much yet this winter, but it's only early January and we're still hopeful. But it's possible. So let's go look at, see if we can see some more of this tephra. Let's walk along a little bit. So it's for these kinds of reasons that I think that studying the Holocene record of hydrologic change out here is in some ways more relevant to modern society than studying the Pleistocene. Although I love studying the Pleistocene, but the Holocene is also very fascinating as well. Okay, I see an old pit that I probably dug. There's lots of old bones on the surface. Jaw bones, some sort of deer or antelope, I'm guessing. Okay, so this looks like something that I probably dug out. I've taken a lot of people here, a lot of field trips. And we'll also make more of them next June. We've got the ILIC. So I think there's probably going to be a tephra in here. Let's check. Pods of it in here. But it's bioturbated, meaning that stuff's digging around in it.